So today we'll start chapter number 9. So this chapter again relates to whatever we have done in the last chapter and earlier. And there are many occasions where people have some theories. Any field you are in, like business, economics, whatever, so people have some theories. Sometimes also they take shape of claims. A manager may claim that in a restaurant, that we serve our guests within 5 minutes. So that could be a claim. Another name we use for theories or claims is hypothesis. Somebody may have a theory that business students at Chartered College of Business prefer chips compared to chocolate bars for snacks. Or it may be that sophomore students in a college sleep less than the recommended 8 hours sleep per day. And another theory could be spending more than 3 hours on social media reduces happiness level for students. So these are like theories. Somebody may claim that this is what is right. These theories, claims, or hypotheses are proven right or wrong based on some test. You want to test these hypotheses or theories and then come to a conclusion whether or not it is correct. How do we test whether this theory is correct or not? The only way is to use data. So we collect data and then check whether these theories hold or not. Now, based on that, you may have a decision in terms of accepting or rejecting that claim or theory. So if a restaurant manager says that we serve our customers in less than 5 minutes, you collect data and you find that the average is actually 15 minutes. So obviously that claim is not correct. So in hypothesis testing, when you are doing it statistically, there is something called null hypothesis that we represent using HO or H0, 0 for null. And this is a tentative assumption. It is a tentative assumption about a population parameter. When we do hypothesis testing, there are always two sides. One is null and other is alternative hypothesis, which we represent using HA, so alternative hypothesis. So what is alternative hypothesis? It is simply opposite of null hypothesis. If you are thinking in terms of theory, claim, or hypothesis, your alternative hypothesis is the one representing claim being made. That goes into alternative hypothesis. So if a restaurant manager is claiming that we serve our customers in less than 5 minutes, then that part becomes alternative hypothesis, and then opposite of that becomes null hypothesis. Hypothesis testing always involves these two hypotheses. And then when you have these two, there are 3 situations possible. You may have HO and HA, where let's say we are claiming that the population mean is less than some number mu 0, that the average time to serve a customer is less than 5 minutes. So this is 5 in that situation, and this is the population mean. So in the long run, that's what somebody may claim. So once you put that claim here, then opposite of this is mu is more than or equal to mu 0. It cannot happen that both are right. After testing, After testing the claim or theory with or hypothesis with data, your decision will indicate whether this or this is right. So only one of them can be correct. So this is the first situation. If you think in terms of distribution, for example, normal distribution, and you are looking at mu less than mu 0 or mu more than or equal to mu 0, so you are only looking at one side of the distribution. You are only looking at one of the tails. If this is the one, you are looking at the lower tail of the distribution. So this is called one-tailed test. Second situation could be you have HO, HA, where mu is more than some mu 0. So that could be a claim. So Tesla may claim that all the vehicles they build for a particular model on a full charge will give 360 miles or more. So that could be a claim that mu is more than this constant 360 or something. So then you have opposite of this, which is mu is less than or equal to mu 0. So this is also one-tailed, but on the right tail. And the third situation could be, so for example, company which produces milk, and they have a gallon of milk, and their claim may be that the weight is always 1 gallon, neither too high or too low. So that could be a situation where mu is equal to some number or mu is not equal to some number. So because you are looking at both sides of the tail, this is called two-tailed test. So those are the three situations you'll come across. So let's look at some examples of this, starting with try it 9.1. So medical trial is conducted to test whether or not a new medicine reduces cholesterol level by 25%. So they are testing this and state null and alternate hypothesis. So mu equals 25% and mu not equal to 25%. So the equal sign is always part of null hypothesis. So that's why cholesterol levels doesn't reduce by 25%. That will always go to HO. Equality is always part of null. So with that in mind, if you look at example 9.2, want to test whether mean GPA in colleges is different from 2. So mu is 2 or not. So mu equals to, mu is not equal to 2. So this is a two-tailed test. Try it 9.2. So we want to test whether mean height of 8th graders is 66 inches. State null and alternate. You have to figure out what should go there for HO and HA. What should we write? Equal, not equal, less than, more than equal to, less than equal to. Mu is equal to 66 or not equal to 66? Equal. So because null hypothesis always includes equal sign. So this will be equal, and by default the other one is opposite of that. Mu equals 66 HA, mu is not 66. So 9.3, we want to test if it takes less than 45 minutes to teach a lesson plan. So whatever we want to test, that always goes to HA. Anything that you want to test or anything somebody claims, so those kind of things automatically go to HA, alternate hypothesis. HO and HA. First we write HA, that mu is less than 45. So once you write that, HO becomes automatically opposite of that, which is more than equal to 45. So in any given situation, if you are doing hypothesis testing, this becomes always your first step. You very clearly write down what is your null hypothesis and what is your alternate hypothesis. Because we are making decisions based on data, these decisions may be incorrect sometimes because we are taking a sample and collecting data from a big population. So whatever decisions we take, sometimes they may be wrong. Like if you have 95% confidence, then the chances are that out of 100 times, 5 times you could be wrong. Those errors in decisions are called type 1 and type 2 errors. There are 2 types of errors that you may come across. Type 1 and type 2. So I'll make a 2 by 2 table here. So let's say your null hypothesis HO is actually true or it is actually false. So only 2 things are possible, either your null hypothesis is true or false. So suppose that is the reality. And then you collect data, use data, and based on the data, whatever analysis we do, that tells us 2 things. Either cannot reject HO or cannot accept HO. So we always talk in terms of HO. So these are the situations possible. So this is reality or actual. So if you are doing any hypothesis testing and your HO in fact is correct, is true, the null hypothesis is true. Let's say you are testing whether students at CCB prefer chips over chocolates. So suppose that is your null hypothesis and it is true that majority of the students prefer that. So if it is true and you collect some sample, you ask 30 people or 50 people, and based on that you say you cannot reject HO, you cannot reject this claim or cannot reject this theory or hypothesis, so that's a correct decision. So your decision will be correct. Similarly, if your null hypothesis actually is false, null hypothesis is that actually they prefer chocolates, so actually it is false, and you collect data, you ask like 50 students, and you find that majority of them like chocolate bars, so you cannot accept HO, you cannot accept that claim or theory, you will be here. So that also is a correct decision. If that happens, that also will be correct decision. So on the diagonal you have actual and your data matches. So this you can think of like reality in the population, and this is based on what you see in the sample. If they match, that's a correct decision. But sometimes it may not. Sometimes this is the reality, but you collect data and somehow in your data you get those samples or people's preferences in such a way that you end up concluding that cannot accept HO. Reality is that it is true, but you cannot accept this, so you are here. So reality is that students prefer chips, but your sample says actually chocolates. So that error is called type 1 error. So that is type 1 error. Also represented by alpha, that you have seen in the last chapter, risk level. And typically that probability of type 1 error captured by alpha is 0.05, which means your confidence is 95% that you are right, but there is a 5% chance that you could be wrong. Most of the times you are making correct decisions, but there is a 5% like chance you may go wrong. When you make 100 such decisions, type 1 error sometimes will happen. It is also called false alarm. So reality is true, but then it is trying to reject it. If you come to this box, reality is that students prefer chocolate bars, and your data based on sample says cannot reject HO. So there is a mismatch. So that is called type 2 error. And the probability of that is represented by usually beta. And we try to maintain it within 10%. You can call this failing to raise alarm. So something is wrong, but your data is not able to capture that. Something is false, but your data is not able to capture that. The claim or the theory or the hypothesis is false, but HO is false, but your sample, the way it is collected, may not be like representative, or maybe some care was not taken. So if you're not able to capture that, so that is your second situation. We are saying that we cannot make this error 0 as long as we are using sample. Some errors will always be there, but the idea is to minimize it. But the problem is you cannot minimize type 1 error and type 2 error simultaneously. You try to reduce type 1 error, your type 2 error will go up. You try to reduce type 2 error, type 1 error will go up. So you may have seen that we are keeping this low compared to this. Depending on the consequences, we want to minimize the type of error which is more dangerous. Suppose the null hypothesis HO is a patient is not sick. So which type of error has greater consequences? Type 1 or type 2? HO. In this situation, what do you think? So if you combine what you see here and this situation, patient is okay or not okay, which one do you think is more serious? Type 1 error or type 2 error? So the reality is true means patient is okay, normal, and false means patient is sick. So there is a problem. It could be anything like a patient is okay, patient has cancer, or patient is okay, patient has some COVID or something like that. And then you do the testing, lab work, and based on that you figure out that you cannot reject HO. So if patient is okay and you are making that decision, that means you are right. Type 1 error means patient is normal, healthy, and then based on the test you find that that patient has a cancer or some other problem, whatever you are testing for. So that is type 1 error. Type 2 error is actually patient has a problem, has cancer or has COVID or whatever problem, but whatever samples you collect, based on that, you are not able to catch that. So that is type 2 error. So which one is more severe in this example? Yeah.
Type 2.
So in this case, type 2, because you are trying to catch. Otherwise, if you think that patient is okay, so doctors will not do anything else. And it may become worse and worse over the years. So in this case, type 2 error is a bigger problem. 9.7 example. A certain experimental drug claims the cure rate of at least 75% for males with prostate cancer. Describe type 1 and type 2 errors in the context. And then which error is more serious? Type 1 error is cancer patient believes the cure rate for the drug is less than 75% when it is actually at least 75%. And type 2 error is a cancer patient believes experimental drug has at least 75% when it has cure rate of less than 75%. And clearly in this scenario, type 2 error contains more severe consequences, just like the previous situation. So if your test is for mean, where sigma is known, so that is one situation that you have seen earlier also. So distribution in this case is going to be normal. And the R function that we use for testing the mean when sigma is known is z.sum.test. That same function that we use for confidence intervals. If we are doing this for population mean where sigma is unknown, then we change its distribution to t, just like the confidence intervals. And the function that we use is tsum.test. And the third situation, as you know, is for proportions. And there we had, in the last chapter, we used normal. And when we use normal, we use z.sum. So in this scenario, you are starting with some null alternate hypothesis, collecting data, doing the testing in those three situations, sigma known, sigma not known, and proportion. And how do we decide? After all that, how do we make a decision? So there's a rule for that. And the rule is rejection rule. So either we do this, we reject HO or null hypothesis if we find that there is a p-value less than equal to alpha. Reject HO if your p-value, p is probability. So based on that testing, your end result is a p-value. And if your p-value is less than alpha, less than equal to alpha, you reject the null hypothesis. Or your rule may be cannot reject is not equal to, so I'm drawing a line across, which means it's not equal to. So cannot reject null hypothesis if opposite of this, like your p-value, this is dash p-value is not less than equal to alpha, you cannot reject. That means HO is true. First one means HA is true, but in hypothesis testing, we always talk in terms of HO. We never talk about like what we do with HA. That is by default. So either we reject HO or we cannot reject HO. So there are only two situations.